Good evening, everyone. I'm Vaishnavi, and today I'll be introducing you to sequence models. So, what are these sequence models? These models are advanced frameworks designed to transform a series of inputs, like the words in a sentence, into a new series of outputs, like a translated sentence in another language. These are especially useful in tasks where the input and output are both sequences that can vary in length. So why do we need this sequence to sequence models? Imagine you're using an app that translates languages or transcribes speech to text. The technology behind such applications often relies on sequence to sequence models. These models help computers understand and generate human like text, and also making interactions with machines makes it more natural. So, how do these sequence to sequence models work? In order to know that, we have to learn about the components of a sequence to sequence model. There are three components in it, which are encoder, context vector, and decoder. First of all, this encoder, it takes part as a input sequence and like a sentence in English and processes it to form a compact representation. In this process, it will capture the essence of what's being said without holding on to the exact words. Next, the context vector, it is a summary of the input sequence prepared by the encoder, which contains of all crucial information needed to generate the output. The next part would be the decoder. This decoder uses the context vector to produce the output sequence, like the translated sentence in French and in a step-by-step process. Here you can see how a sequence to sequence model works. First, the process starts with the input sentence being fed into the encoder's RNN. As the sequence passes through each layer, the RNNs process the information and pass it along to the next layer. After the last encoder RNN, a summarized version of the input sequence, which is often in the form of a context vector, is passed to the decoder. Then the decoder begins generating the output sequence. So it generates one element at a time, which uses the context provided by the encoder to ensure that the output is relevant and also accurately reflects the input sequence's information. So this model is highly effective for tasks where the input and output are sequences that can vary in length and structure, making it a powerful tool for various applications in natural language processing and beyond. Next, we'll look into the applications of these sequence to sequence models. Sequence to sequence models are behind many systems you interact with daily. For example, Google Translator for the language translation or voice-enabled devices that understand the spoken commands. So they are fundamental in machine translation, where the transformation of text is done from one language to another. Next, speech recognition, when you convert the spoken language into written text, then you can use it in chatbots, where simulation is done for a conversation with the humans. Next, we'll look at attention mechanism. So what is this attention mechanism? In human interaction, we focus more on certain words than others for understanding. Similarly, the attention mechanism in sequence to sequence model helps the system focus on relevant parts of the input when generating the output. This makes the model more efficient and accurate, like highlighting keywords in a sentence to better grasp its meaning. So let us understand it with the help of an example. Let's say you're seeing a group photo of your first school. Typically, there will be a group of children sitting across several rows, and the teacher will sit somewhere in the between. Now, if anyone asks you the question, how many people are there? How will you answer it? So you simply start counting heads, right? You don't need to consider any other things in the photo. Now, if anyone asks a different question, like who is the teacher in this picture? Your brain knows exactly what to do. It will simply start looking for the features of an adult in the photo. The rest of the features will simply be ignored. So this is called as attention, which our brain is very adept at implementing. Next, we'll look at the transformers. Transformers are advanced models designed for converting sequences of data, such as sentences, from one form to another. These were introduced in the year 2017. These models also excel at understanding relationships in data over long distances and are widely used in tasks like language translation and document summarization. The key features of these transformers are self-attention mechanism, which means that it allows the model to identify the importance of each word in a sentence to better understand the context. Then we have encoder and decoder stacks. So it is composed of multiple layers. First, the encoder processes the input text and then the decoder generates the output. Then we look into multi-head attention. This feature allows the model view the input from different perspectives simultaneously and also enhancing the comprehension. Next, we look into positional encoding, which means that it provides the model with information about the order of the words in a sentence. Next, we have feed-forward networks and normalization. These components refine the data and ensure that the model trains efficiently and effectively. So with the help of this transformer, we can handle complex language tasks by analyzing the entire context of the input and also making them highly effective for generating accurate and contextually appropriate outputs. So this is the model of a transformer. Here you can see different parts like the input processing parts, the main components, decoder processing, and output generation. In input processing, we have input embedding, and positional encoding. In the main components, we have multi-head attention, feed-forward networks, and in decoder processing, we have masked multi-head attention. And for the output generation, we use linear and softmax layers. So what are these layers and models? So the input embedding is nothing but it converts our input words into the numerical data. Next, the positional encoding in the input processing, it adds information about the orders of the words. Next, it passes through the main components, which are multi-head attention and feed-forward networks. This multi-head attention, it helps the model focus on important parts of the input so that we'll get a better understanding. Then we have feed-forward networks. It is used to simplify the networks that further process the data independently for each and every word. Next, we'll go to the decoder processing. So this is done by the masked multi-head attention. This part ensures that the predictions which are made that they are based only on the previously known outputs and not the future ones. Next, the last part would be the output generation. For this, we have linear and softmax layers, which are used to transform the decoder's output into probabilities of possible next words. So by using this model, the components to process the input and generate output sequentially, refining and understanding and output generation at each step through multiple layers. So this structure enables effective handling of language-related tasks like translation or text generation by focusing on context and sequential data processing. So from this presentation, we can say that sequence-to-sequence models are transformative in how they enable fluent communication between humans and machines, and also by simplifying complex language tasks with remarkable efficiency. So by mimicking aspects of human cognition, these models enhance our interaction with technology, making it more intuitive and effective. So this is about sequence-to-sequence models. Thank you.